This is Physical Chemistry, Part 3, Quantum Chemistry, Chapter 17, Commuting and Non-Commuting Operators, Section 17.1, Commutation Relations. If two operators have a common complete set of eigenfunctions, we say these two operators commute. For example, in quantum mechanics, the momentum operator and the kinetic energy operator commute because they do have a common complete set of eigenfunctions, e to the power of plus minus ikx. K times h bar is the magnitude of the momentum of the system that's associated with this wave function. Now let's define commutator. The commutator of two operators A and B is this. It's AB minus BA. AB minus BA is the commutator of two operators A and B. We can also include this A and B inside this pair of square bracket. So this is the shorthand notation for the commutator of A and B. If the commutator of A and B is 0, then we say A and B commute. Now let me give you an example. We will prove this momentum operator and this kinetic energy operator commute. So we write out the commutator here. And then when we evaluate the value of the commutator, we need to apply this to an arbitrary function f. So that's what we do here. And then we copy the definition of the commutator. The commutator AB is AB minus BA. So I have A here, B here. So this is A, B, F. And this is B, A, F. All right? And then after we evaluate these two terms, they happen to be exactly the same. And they cancel. The result is 0. So we say the commutator of the momentum operator and kinetic energy operator is 0. We say the momentum and kinetic energy operators commute. And that means we can determine the momentum and kinetic energy of the same system exactly at the same time. Now you may wonder, isn't AB always equal to BA? You're right if you're talking about numbers. Yes, AB is equal to BA if you're talking about two numbers. But if you're talking about two operators, they can be different. If you're talking about two matrices, AB can be different from BA. The order matters. So now let me give you another example. The position operator and the momentum operator. We will evaluate the commutator of the momentum operator and the position operator. We do the same procedures. So this is our A, this is our B. So we have A, B, F minus B, A, F. They share a common factor, negative IH bar, so it's here. And then we need to take the first derivative of XF and then subtract X times the first derivative of F. Using the product rule, we get two terms here. Over here, we have only one term. These two cancel. So in the end, if you apply this commutator to F, the result is not 0. The result is a constant times F. Therefore, this commutator is equivalent to a constant operator. And that constant is negative IH bar. So we say this commutator is negative IH bar. It's not 0. The position and momentum operators do not commute. We cannot measure the position and momentum exactly at the same time. And that's the Heisenberg uncertainty principle. This can be proven easily from here. Now I just want to remind you, if you change the order here inside the commutator square bracket, if you do X in the front, if you place this momentum operator on the right, and then the sign of this will change. Because if you swap A and B, it will become BA minus AB. All right, the sign changes. Section 17.2, the Sturm-Gluck experiment. So in this experiment, I will show you this experiment. So we have a bunch of electrons passing through this magnetic field, and half of these electrons spin about its z-axis in the clockwise direction, half counterclockwise. All right. So when they pass this magnetic field, half of the electrons will change their direct trajectory upward. Half will change their trajectory downward. All right. So this is a simple experiment. Now let's look at a more complicated experiment. We have 3 magnetic fields. So again, we have this a beam of electrons passing this magnetic field. Again, half going up, half going down. All right, but now we will place another magnetic field in the x direction and allow this clockwise electrons to pass through this magnetic field. And then the result is not surprising. We have half away from us and half close to us. Now we're just look at these electrons closer to us, and we put them into another magnetic field, again in the z direction. And now it's surprising. Now again we have half going up, half going down. So look at here. We pre-selected the electrons moving downward. So supposedly all of these electrons should be moving downward. But then if you allow these electrons to pass through this magnetic field in the z direction, again, half going up, half going down. All right, so let's pick these electrons, all these electrons, and allow them to pass through another magnetic field in the x direction. Surprisingly, again, you will find half of the electrons move away from us, half of the electrons moving toward us, despite the fact that we have pre-selected the electrons that move toward us. So why is that possible? In quantum mechanics, when you measure any property of a particle, you are applying an operator to that particle. So right now, we are applying the angular momentum operator to the particles. And specifically, we are applying the z component of the angular momentum operator to those electrons. All right? And there are 2 possible eigenvalues, negative h bar over 2 and positive h bar over 2. So we can select these electrons with a positive h bar over 2 eigenvalue. And then we allow these electrons to pass through this magnetic field. When you do that, okay, this is very important. You are applying the x component of the angular momentum operator to these electrons. You are collapsing the wave functions of these electrons and force them to adopt an eigenfunction of the x component of the angular momentum operator. It can be positive half, it can be negative half. That's why. And now these electrons are all eigenfunctions of the x component of the angular momentum operator. So you pass these electrons in this z direction magnetic field. Well, these electrons are not an eigenfunction of the z component of the angular momentum operator. So again, this magnetic field will collapse these wave functions and force them to adopt one of the 2 possible eigenfunctions of the z component angular momentum operator. And again, it's going to be just negative half or positive half. So we are actually applying 3 different operators. Well, actually, these 2 operators are the same. So we are applying the z operator to the electrons and force them to become one of the 2 possible eigenfunctions of the z operator. And then we are forcing these electrons to adopt a new eigenfunction of x operator. And finally here, again, this measurement will collapse the wave functions of the incoming electrons and force them to adopt a new eigenfunction of the z operator. So that's why quantum mechanics is confusing. But in the end, you just need to remember this. Whenever you are measuring a physical property of a particle, you are applying the corresponding operator to that particle. And that may result in the collapse of the wave function of the particle. The result is this. After the measurement, the particle will likely have a new wave function. That new wave function has to be one of the many eigenfunctions of the operator associated or corresponds to the measurement. Section 17.3, the Heisenberg uncertainty principle. I think you learned this in general chemistry. The uncertainty of momentum times the uncertainty of position is at least 1/2 of h bar. H bar is the reduced Planck constant. I think h bar is roughly 1.054 times 10 to the power of negative 34 joules second. In the y or z direction, we have similar equations. However, we can measure the momentum in the x direction and the position in the y direction simultaneously and exactly. So these two uncertainties, if you multiply them together, it can be 0 because these two operators, the momentum operator in the x direction and the position operator in the y direction, they do commute. So we can prove this. Again, they do commute because y does not depend on x, x does not depend on y. All right, so in that case, again, you can measure the momentum of a particle in the x direction and its position in the y direction simultaneously. Now let's look at some other forms of this uncertainty principle. If you are observing the rotation of the particle, the uncertainty of the angular momentum times the uncertainty of its position. In this case, we use the angle to specify the position of the rotating particle. So again, the product of these two uncertainty values is going to be greater than or equal to 1/2 h bar. Another equation here, well, it's inequality, but it's just if you are measuring the energy of the system within a time period delta t, the uncertainty of the energy measurement times the duration of the time period is at least 1/2 of h bar.